Good morning, everyone. This is Han Hu from Microsoft Research Asia. The title of this talk is Swin Transformer and 5 Reasons to Use Transformer and Attention in Computer Vision. Now, everybody knows transformers. It was invented 4 years ago. During the last 4 years, it has refreshed the NLP field, and is also the current dominant architecture in this field. It's so successful in NLP, encouraging researchers to think about a question: what is the role of transformer for computer vision? Let me directly pose the answer. We think it will also refresh and dominate computer vision. We are confident on this answer because transformers have achieved very strong performance on 3 important vision benchmarks since the end of the last year. Let's say the first benchmark, ImageNet 1000 image classification. This task is the most important benchmark in computer vision to the date. The task is to categorize images into 1000 classes. This figure shows the best methods across years. Before the last October, all methods are based on a thin backbone. Now, transformer architecture surpasses all previous approaches, concretely by VIT from Google. Now, most top methods are based on transformer architecture. What is VIT? Please see this illustration. It's very simple. An image is first partitioned into 16 by 16 patches. Then, a standard transformer architecture is applied on these patch features. The transformer encoder is almost unchanged from that used in NLP, with the same depth, same number of channels, and the same number of heads. Though very straightforward and simple, the performance is very strong. It performs the state-of-the-art at the time. It's also the leading algorithm on the ImageNet 1000 benchmark to the date. While ImageNet 1000 image classification is an image-level task, let's say 2 other most important vision benchmarks at region level and pixel level. Firstly, local object detection, a task to produce the location of objects in image. This figure shows the best methods across years. Before this March, all methods are based on a single backbone. Now, transformer backbone surpasses all previous approaches, concretely by Swin transformer. Now, all top methods are based on Swin transformer. Let's say another benchmark about segmentation, a task to produce predictions for every pixel. Also, before this year, all methods are based on a single backbone. Now, transform backbone surpasses all previous approaches by a large margin, concretely by a Swin transformer also. So, what is Swin transformer? It's basically an architecture which introduces some good priors for visual signals into the standard transformer architectures. The good priors include hierarchy, locality, and translation invariance. Both the ideas of Swin transformer and VIT are very simple. However, the road towards these architectures takes 4 years. In fact, soon after transformer was invented in the NLP field 4 years ago, the computer vision community has started to tame this architecture for computer vision. Or more concretely, the community discovered more and more merits of this architecture year by year. The first 2 merits being explored is the general modeling capability of this architecture and the complementary of transformers or attention layers to convolution layers. These two merits are first explored in two pioneer works in November of 2017. The third merit is its strong modeling power explored since April 2019. The fourth merit is that it can benefit the collection of vision and language, which was explored since early this year. The fifth merit lies in its ability to be scaled up in both model size and data size. In the following, I will describe these 5 reasons more detailedly, as well as introduce related works. In particular, I will also introduce Swin transformer in detail, which is a general-purpose backbone for computer vision. It basically exploits the third merit of transformer. Let's go to the first reason to use transformer in computer vision. That transformer owns general modeling capability. In fact, transformers can be treated as a general graph, where all concepts and their relationships can be modeled by a graph. The concepts can be either concrete or abstract. The general modeling capability is also partly ascribed to the verification principle in building relationships between graph nodes. Please see the right illustration. Thanks to the verification philosophy, transformers can process image patches of different scales and even process multi-model data such as text and images. This general capability enables transformers to model all kinds of relationships in computer vision, such as pixel-to-pixel, object-to-pixel, and object-to-object relationship, which cover almost all vision applications. Here is a pioneer work in CVPR 2018. The work aims to model the relationship between objects. Please see this image patch. I believe it's difficult to figure out what it is by seeing this patch alone. However, if we see the context, it's easy to recognize the patch as a baseball glove. After we note there is a baseball player holding it. In previous years, there are no good networks to model this kind of relationships. However, the self-attention module in transformer can be leveraged to conveniently and effectively model this relationship. Please see this illustration. The input and the output of this module have the same dimension, and this module can thus be applied in place in many places of a network. We also made some adaptations. For example, we additionally account for the relative position in attention computation, which is proved important in the object detection application. This module also helps to create the first fully end-to-end object detector. Concretely, the module is inserted into 2 steps of a fast-acting object detector. Please see the red blocks in this pipeline. Firstly, it's inserted in the instance recognition head. Now, the objects can be jointly recognized instead of processed separately as in previous methods. The second is to do duplicate removal. In previous methods, duplicate removal is usually achieved by a handcrafted non-maximum suppression method. By this self-attention module, we can make this step end-to-end learnable. Another work I would like to mention is from Facebook AI Research called DTR. It directly applies the encoder-decoder architecture of transformer to the object detection problem, which is also an end-to-end object detector. Next, we introduce the second reason to use transformer in computer vision. That is, The transformer layer or attention layer is complementary to convolution layers. Convolution is criticized as being too local, that the convolution layer has difficulty extracting long-range pixel-to-pixel dependency. Please see this illustration. For this output, even by stacking 4 zeros, only pixels within a very short distance are modeled. Other pixels are not. The transformer layer is complementary to this local convolution layer, that it can see all input nodes by a single layer. A pioneer work is the local networks proposed on CVPR 2018. It applies self-attention modules to encode dependency between distant pixels in complementary to the local convolution layers. Please see this illustration. A football pixel and the human body pixels are distant from each other. Their dependency is hard to be captured by convolution networks. Nevertheless, it can be conveniently modeled by a single self-attention module. In its work, the self-attention modules are sparsely inserted into a ResNet to complement the local convolution layers. For example, this is a ResNet. In object detection, one block is inserted at the stage 4 of the ResNet. The local network is very successful. It can broadly improve existing action recognition, object detection, and semantic segmentation algorithms. In common understanding, the self-attention formulation models pairwise relationship, for example, the dependency between pixel pairs. To learn meaningful pairwise dependency, we expect different query points affected by different key points. This is an illustration. The left image shows 2 query pixels at different locations. A red query is on a car, and a yellow query is on a fire hydrant. The right image shows some key points colored in green. We expect the car query pixel mainly affected by these 2 key points, and we expect the fire hydrant query pixel mainly affected by these 2 different key pixels. But what does the self-attention module really learn? Unlike expected, we find different queries in the left image are usually affected by the same key pixels in the right image. This means the self-attention module degenerates from query dependent to query independent. It behaves more like a unary model instead of a pairwise model. We show some real examples from the tasks of object detection and semantic segmentation. These images are the attention maps of all key pixels to different query points, where the query points are marked by the white crosses. And for the attention maps, the warmer the color is, the higher the attention similarity is. We can see that the attention maps of different query points are very similar, especially for object detection. This also indicates that the self-attention model degenerates to a unary model. We found this degeneration phenomenon in 2019. This phenomenon also indicates that the local block can be simplified by explicitly leveraging the degenerated formulation. Hence, we propose GC block, which reduces 2000 times computation and 20 times module size compared to local networks, where the accuracy is unchanged on local object detection. We further study the reason leading to this degeneration phenomena and propose a disentangled self-attention module to address this issue. Next, let me show the third reason to use transformer, that is, transformer's strong modeling power due to adaptive computation. The convolution layer is criticized to have low efficiency. In fact, convolution performs a template matching using fixed filters across all image positions. Please see this image. There are 3 boards with slightly different head poses. With a convolution layer, we need 3 channels to encode these 3 board heads, which is inefficient. Other than using fixed filters across image positions, transformer layer uses adaptive filters with the filter width determined by composability of 2 pixels. In this way, potentially we need only 1 channel to model different board head poses. This merit encourages training transformer as a backbone for computer vision. If succeed, the impact to the vision field will be very significant, as the vision backbone is used in almost all vision tasks. The first attempt was made in 2019. The most popular backbone network in computer vision is ResNet at the time. We replace all convolution layers in ResNet with transformer layers, maintaining the same computation complexity. The resulting network is called local region networks. Here, we compare this network with ResNet on ImageNet classification. The blue curve shows the results of ResNet, which is based on convolution layers. The orange curve shows the results of our local region networks. The transformer-based local region network is 2.7% better than ResNet. However, though theoretically the same efficient than ResNet, it's much slower in real usage. A main reason is that different queries use different case sets, which is unfriendly to memory access. Please see this illustration. For the center point Q, we use all pixels inside this red window as keys. For query at another location, for example Q prime, the window will be changed to centering on this new query. Because Q and Q prime use different case sets, the real speed of this approach is limited. Because of this, it's not practical to work as backbone. The situation was changed by a milestone work from Google, VIT, as we have introduced at the beginning. In addition to the impressive results on image classification, it has another interesting behavior. Please see this table. On a TPU, it's even 50% faster than ResNet with similar flops. We found the main reason of its fast real speed is that the self-attention computation is performed globally, and thus all queries share the same case sets. However, this approach doesn't consider the good priors in computer vision, and we argue it could be suboptimal for computer vision applications. We thus consider introducing good priors of computer vision into the architecture design, and the resulting architecture is called Swin transformer. Swin transformer basically equals transformer plus good priors for visual modeling, such as hierarchy, locality, and translational invariants. Please see this illustration. It's a standard transformer architecture used in VIT. In this illustration, each gray box indicates the image patch, and the red window indicates the scope of self-attention computation. In VIT, the computation is performed globally over an entire image. In Swin transformer, we introduce several priors, which will be discussed one by one in the following slides. The first good prior is called hierarchy. Please see the left figure. In computer vision, no matter how large a fat cat is, it's still a fat cat. The vision algorithms are usually required to process these objects of different scales. This goal can be well achieved by a hierarchical structure. Please see the right figure. It starts with smaller image patches, for example 4x4, and builds hierarchical feature maps by merging image patches in deeper layers. The second good prior is called locality. Different from natural language, visual signals are highly correlated in spatial. Locality has proven very beneficial in modeling such high correlation data. Locality can also make the complexity linear to image resolution, instead of quadratic as in VIT. For example, please see the left image. There are 256 patches, and the computation of VIT is in quadratic complexity with respect to the number of patches. Please see the right image. When we partition an image into 4x4 windows and perform computation within each window, the complexity will be reduced by 16 times. An important feature of our locality is that the windows are non-overlapped. This design ensures our fast speed in real computation, particularly when compared to the traditional standing window approach. Please see this illustration. The left figure shows the locality by standing window. As we discussed before, different queries have different key sets, which is friendly to memory access, and the real speed is thus not good. The right figure shows the illustration of our non-overlapping windows. Different queries within a same window will share a same key set, and is 3 times faster in real speed. Another important feature is that we enable cross-window connection by shifting window partitioning in successive attention layers. This makes this approach as effective as the standing window methods, or even better due to regularization effects. The third good prior is called translational invariance. In computer vision, we expect a fat cat at arbitrary location is recognized as a fat cat. Moreover, relative position bias plays a more important role in vision than in NLP. We implement this prior by adding a bias term to the similarity computation. An interesting point here is that we don't guarantee fully translational invariance due to long overlapped windows. We call it translational semi-invariance. Interestingly, we find this semi-invariance performs as good as fully translational invariance in experiments. Based on these good priors for computer vision, we design the architecture of Swin transformer as shown in this figure. It basically follows ResNet to have 4 stages, with each stage the same resolution as that of ResNet, to facilitate application to downstream tasks. In each stage, there are repeating Swin blocks, with each block the same as that of transformer architecture, but with attention computation limited within each shifted window. Since backbone networks are required by almost all vision tasks, Swin transformer can be applied to various visual applications. We demonstrate its power on several common benchmarks. The first is object detection and instrumentation on COCO. Previously, the best approach is efficient det plus copy-paste, published on this year's CVPR. Now, all the top 3 records of this benchmark is built on Swin transformer. The current best record is 60.6 MAP, which is 3.5 higher than that by copy-paste. For instrumentation, the best record is 52.4 MAP by Swin transformer, which is 3.3 higher than previous best record by same models. The improvements over previous backbones are universal. For example, on these 4 detection methods and 3 different model sizes, Transformer performs consistently 3 to 4.5 points over ResNet with similar model size and computation. The second application is semantic simulation on ADE20K. It also surpasses all previous models by a large margin. That is, this model is 5.5 higher than the previous best seen model. On ImageNet 1000 image classification, although VIT is leading the leaderboard, Swin transformer is 3.5 points better than VIT with similar model size, computation, and pre-trained dataset. Swin transformer not only works well on images, it's also good for videos. We extend the Swin transformer as a video backbone by introducing an additional time dimension. And 2 major video benchmarks, Kinetics 400 and Kinetics 600, Swin transformer achieves SOTA, surpassing previous best method Vivid by a large margin when using the same pre-training data. On Kinetics 400, it achieves 84.9, which is 3.6 better than Vivid. On Kinetics 600, it achieves 85.9, which is 2.9 better than Vivid. Let's go to the last 2 reasons to use transformer in computer vision. The first reason is that using transformer where net vision part has similar architecture as net of language part. It will benefit visual language learning as illustrated in this OpenAI's work clip, where VIT performs better than native ResNet and similar computations. The fifth reason is that the vision transformer seems able to be scaled up to very large model and very large data. In fact, a work publicly available just 1 week ago by Google has demonstrated a 2 billion model to perform state-of-the-art on ImageNet 1000 image classification. Finally, here is a summarization of this talk. Since the invention of transformer in the NLP field 4 years ago, it has quickly dominated the NLP field in architecture design. In computer vision, the power of transformer was gradually unleashed during the last 4 years by exploiting 5 merits of transformers. The first merit lies in the general modeling capability. I list here 6 related works which explore transformer or attention layers for visual relationship modeling. These papers marked in red are the works of ourselves. The second merit is the ability to complement convolution, which is too local. I list 3 related papers here which exploit this merit. The third merit is its strong modeling power. This merit encourages stronger transformer backbone than convolution backbones, typically include VIT and Swin transformer. The fourth reason is that it can benefit collection of vision and language due to unified modeling. The fifth reason is the ability to be scaled up in both model size and data size. Given these strong 5 reasons, we believe that transformer will also refresh and dominate computer vision, like what has been observed in the field of natural language processing. This is the end of this talk. Due to having used up my assigned time, I will skip the voice Q&A session. If you have questions, please post them in the message channel. I will respond to you in that channel. Also note, this is not a survey. There are many great works related but not mentioned in this talk. I feel sorry about that. Thanks for your attention.